Hello, good people. Welcome to yet another episode. And this video is going to be another hands on project where we get a chance to practice and learn something new. So, today's video is going to focus on Deep Contextual Bandit, which is also a multi armed bandit algorithm that takes into consideration state or context information. And I have already implemented this, but I'm going to implement from scratch with you so that you understand every step of the way. Now, if you have followed the previous hands-on project on multi-armed bandit algorithm, you realize that there is no point where we took into consideration any state information or context information. And by state or context, what I mean is any information, any piece of information that should influence the action that the agent takes. So up until this point, we've not taken into consideration any kind of information that looks like that. And what our agents have been doing is mostly to pull arms and steady their reward rate and continuously explore and also exploit. So by exploiting, it pulls the arm that it has learned to have the best pay rate so far. And by exploring, it also gets the chance to try out newer arms that it hasn't tried often. And so, yes, this classical multi-armed bandit algorithm has its own applications. And by the way, if you look at the notebook I shared with you, I have included newer implementations or newer MAB algorithms that I haven't explained, and I'm going to do that later. So I have, I think we ended on epsilon greedy, and I have included softmax selection and also Thompson sampling, which is something that I'm going to talk about later. Okay, so let's go ahead and create today's notebook. So in today's video, I'm going to use most of the things that I've taught on PyTorch, especially in the last two videos. So if you haven't watched them, make sure you watch them. So our usual import, I'm going to import torch. I'm going to import torch.nn as nn. I'm going to import torch.optim as optim. This is where we get our optimizers. And I'm also going to import torch.nn.functional as f, and I'm going to import matplotlib.pyplot as plt, and I'm going to add my magic matplotlib inline. Okay, so these are the usual imports that we always see, nothing new here, and basically just setting up our notebook. Let me go ahead to rename this notebook to Deep Contextual MAB. Okay, so like I explained at the start of the video, you can see that all the MAB implementations that we've had so far, they didn't take into consideration state information or any context information that influence the actions that the agent takes. But the thing is, in reality, before the agent takes any action, there are states or context information that it can take into consideration to affect the action that it takes. For example, let me give you a very raw example. In our implementation of the MAB, I used a casino as an example where you are standing by a multi-armed machine and then you pull the arms and you get certain rewards, and your objective is to maximize your reward in the long term. Now the question is, if you just stood by the machine and then you kept pulling the arms randomly like this random agent did up here, you end up not getting the best reward that you can ever get. And so we came up with a better approach where we're doing epsilon greedy agent, where for a certain percentage of time we explore, which is to try new things, and for a certain percentage of time we pull the arm that we know to be the best so far. Now the question is, if the environment is not static, or if the actions are supposed to be influenced by certain state information or context information, then this agent is not going to perform very well. For example, what if the machines have been configured such that on Christmas evening, let's say arm 1 is actually the best arm, and on any other time arm 2 is the best arm. If you go by this approach, you never get to get the best reward on Christmas evening, because you never take into consideration the status information. So this is a very vague example that I wanted to share with you to prepare your mind to know what I mean when I say context or state. I'm going to give you more concrete examples. So I'm coming back to this notebook, and to talk more about state, let me use this example to help you understand it. I am sure you see a lot of adverts on different websites that you visit. And I'm also sure you agree with me that most of these adverts that you see on the various websites that you visit are very similar. And it almost feels as if the various social media websites out there, or different websites out there, especially even e-commerce websites out there, share information with all these other websites that you visit. And the truth is that the website builds a digital footprint of your online behavior, of your activities online. And that becomes a context information that they know about you. So if you are somebody who is interested in AI, you are interested in technology, you are interested in football, you are interested in religion, you are interested in music, or you are interested in even a particular musician, then they are able to come up with a context information that contains everything that they need to know about your digital footprint, or your online behavior. And this context is what influences the advertisement that you see, because the goal of these advertising agencies is to increase the click-through rate of the advert. So they don't just want to show adverts randomly for you to see. For example, if I'm running 5 e-commerce websites and I want to promote the product on other sites to people who are visiting my other e-commerce sites, it doesn't make sense for me to show things randomly. For example, if on one of my e-commerce sites I sell microcontrollers, so I sell Arduinos, I sell Raspberry Pis, I sell ESP32s and stuff like that, I sell electronic components, and on another site I sell shoes, okay? Ask yourself, does it make sense for somebody shopping on my electronics website to see adverts relating to shoes that are being sold on my other e-commerce website? And the answer, I believe you agree with me, is no, because there isn't that direct connection between someone shopping on an electronics e-commerce website and someone being interested in buying shoes on another e-commerce website. However, if the user visited my site where I am selling dresses, then it makes sense for me to show the person some adverts that they can click on to come to my other e-commerce website where I'm selling shoes, okay? And the reason is that, yes, if someone is buying a dress, then there's a high probability that the person also wants a shoe to go with that dress that they are buying, okay? So this is the simple technology that is powering all these advertisements out there. Basically, they form the context information about you that becomes the state, and then their reinforcement learning agent has the sole responsibility of showing you adverts that you are highly likely to click on, so that the purpose of the advertisement is served. Because the reason why people serve advert is to get you to click on and actually land on their page and hopefully buy something from there. So in this particular scenario, you can see that it doesn't make so much sense for you to randomly show adverts on e-commerce websites regardless of whoever is visiting. So what we are going to learn today is how can we take this context information and use it to guide the actions that the agent is going to take. And in this particular implementation, we are going to use a neural network to learn the association between the context information and the optimal actions to take based on the context information that you know of. Okay, now I'm going to copy some code that I've already written here. I call it the running mean, which is also something that smoothens a set of data. And this is not the focus of the video, so I'm not going to focus on explaining everything here to you, but basically it's going to help me to plot a smoother graph of my rewards at the end of everything. Okay, now Before we start talking about um, the contextual bandit in detail, there are two concepts in machine learning that you need to understand before you'll be able to appreciate this video very well. The first one is one-hot encoding, and the second one is softmax. So I'm going to take time to explain these also to you, and once you've understood them, we can go ahead and implement the deep contextual multi-amp bandit algorithm, which is the focus of today. Okay, so let's talk about one-hot encoding. What is one-hot encoding? So when it comes to machine learning, data that is used in machine learning, specifically categorical data, it doesn't help to feed categorical data directly into a neural network, because neural networks has the potential of associating importance with the categorical information, especially when you encode them as integer. For example, let's say you are building a neural network that is going to predict how long a car will last based on its model. This is a very vague example, but it's just supposed to help you understand. So let's say we have three cars. We have Honda, we have Toyota, and we have VW, okay? And then you encode Honda as 0, you encode VW as 1, and you encode Toyota as 2. If you feed this information directly into the neural network might learn to associate the categorical labels with levels of importance. So you can see that the car that has the label 0 will be treated as not so important, and the car that has the label 2 will be treated as most important by the neural network. It is just the nature of how neural networks work because of the linear transformation, the calculation of the linear transformation that goes on in there. So one way to mitigate this problem is to do something we call one-hot encoding, okay? And one-hot encoding is very simple. If I have 4 categorical labels and I want to one-hot encode them, what I basically have to do is I come up with a vector which is all zeros except the particular label where I want to indicate that this particular vector refers to this label, then I set 1 over there. I think this is best explained through an example. So I'm going to write code and then we will see what I mean with all these things. Okay, so I'm going to create a function called one-hot-encode. So one-hot-encode, what is going to take is, it is going to take a position or even a number, and then I'm going to say the dimension. It's going to take a position and a dimension. And this is what the one-hot encoding is going to do. So we first of all start by creating a vector of all zeros, okay? So np.zeros, and what's going to happen here is I'm going to create zeros of the dimensions dim, okay? And then for vec position, I set it to 1, and let's return vec. Let's return vec over here. Okay. All right, so let's print out the one-hot encoding for 0 and see. So one-hot encode 0, and I'm going to also let me do all the way to, let's say, 3 or 4. So 0, 1, 2, and 3. Okay, and we need to state the dimension. The dimension should be the total number of categorical labels that you have. And because I'm doing for just 4, I'm going to set it to 4, 4, 4, and 4. And let's print out what we get. Okay, so you can see that the one-hot encoding for 0 on a dimension of 4 is 1, 0, 0, 0. That of 1 is 0, 1, 0, 0. And 2 is 0, 0, 1, 0. And 3 is 0, 0, 0, 1. So basically what is happening here, let me reduce the font size of this guy. Something changed here. Let me just reset this guy. Okay, great. And let me try to bump up the size a bit so that it is big enough for everybody to see. All right, so what is happening here is I have this one-hot encode, and what the one-hot encode is doing is basically come up with a vector which is all zeros except the item at the position that I want to encode. Then I set it to 1. And I have already explained to you why you need to one-hot encode things. And the reason why I'm teaching you one-hot encoding here is we will need it in the neural network that we'll be implementing for the Deep Contextual Bandit algorithm. Okay, so that is it with the one-hot encoding. The next thing we want to talk about is softmax. Okay, and what a softmax function does is it helps you to turn a list of numbers into a probability distribution. And once again, this is best explained through an example like I always do. So I'm going to write a code and then I'll explain to you what it does. And the formula for softmax is very simple. So you basically just divide every number by the summation of all the numbers in the list, and that is how you turn them into a probability distribution. But for our use case, we are going to introduce another parameter called tau, which is also known as the temperature. And the value of tau, the value of the temperature, determines how much the softmax function is going to exaggerate the differences between the values that you give to it. So that's enough talk. Let's implement softmax. So I have softmax here. I'm going to give it data and I'm going to give it tau. I'm going to set it to 1.2 or 1.2 by default. And what's going to happen is I'm going to say, I'm basically going to say my softmax is equal to, you take the exponent of data divided by tau, okay? And then what you do next is, so basically you have the exponent. Let me write my bracket well so I don't confuse you. So you just take exponent of data divided by tau and you divide that by the sum of this same expression here. Okay, so you can say np.sum. If you want to be very efficient in your implementation, then you want to evaluate this particular thing just once so you can reuse it. But at this point, I don't really care. So I'll just return my softmax. Okay, so here you have the function softmax. And what we are going to do with this softmax is, first of all, we're going to see an example of how softmax will work. So let's print the softmax of np.array. What if I have an array that has 1, 1, 1, and 1 in there? What is a softmax? So if you have an array that contains 1, 1, 1, 1, then if you turn it into probability distribution, then each one of them has 25% chance of being there. So 0.25, 0.25, 0.25. What if I change this to, let's say, 2? What happens is the value, the softmax value for 2 should be higher than that of the rest, because see, this is 2, and so when I turn them into probability, I expect that what I find here, this is 0.434 and the rest are 0.1886. And so basically that is how the softmax function works, and this is also something that you see a lot in the subsequent videos that will come, but I'm teaching you this because we need it once again in this implementation of the Deep Contextual Bandits that we're going to talk about in this video. Okay, so all the preparatory works have been done so far, and so the next thing we want to do is to go about creating a simulation environment where we can practice this Deep Contextual MAB algorithm. So let's go ahead like we did in these videos. I started off by creating an environment with you. And the reason why having a simulation environment is important in reinforcement learning especially is because, one, reinforcement learning takes a long time to learn depending on the type of algorithm that you are choosing. But because most of the learning is happening through trial and error, it takes quite some time to learn. And two, you don't already have data that you have captured, unlike what you do when you are building algorithms for supervised learning, where you have tens of thousands of already acquired and cleaned data that you use to train the model. In the case of a reinforcement learning algorithm, it captures the data through exploring and trying things in the environment, and so this also increases how long it takes for it to learn. And also, it becomes expensive to do reinforcement learning if you don't have a simulation environment. For example, consider companies that are working on self-driving cars, and let's say they just write their algorithms on a real car and put the car on the road and ask it to drive by itself. The problem is it is going to be very catastrophic because in the start, the algorithm or the agent driving the car doesn't know anything about driving. So you expect that majority of the time the car is going to run into other cars or other properties or even take human life because it knows nothing about driving. And so it becomes very expensive if you put reinforcement learning algorithms out there in the real environment for them to learn. And so these are why it is important for us to have simulation environment to be able to simulate how our algorithms work. Okay, so we are going to create our simulation environment, and I will be explaining the code as we progress. Okay, so I'm going to create a class called environment, and it's going to inherit from object. Okay, and we're going to create a constructor underscore underscore init underscore underscore and then self, and then this is going to be the number of arms. So the number of arms are the different set of actions that our agent can take, and for simplicity we are also going to assume that the number of the different states that our agent can be in is also determined by the number of arms. But if you are applying it to your own problem, it doesn't have to be the same. Okay, the number of states must not be the same as the number of arms, and in reality mostly it's not going to be like that, but for the sake of simplicity I'm leaving things so that the number of states is equal to the number of arms. And from this point, when I say arms, I mean the different set of actions that is possible for the agent to take. Okay, so I'm going to say self.arms is equal to arms. So in your case, you need to figure out what arms are. For example, if I am building this reinforcement learning agent to help optimize click-through rate on adverts, then my arms is going to be the different number of adverts that I have in my database. Okay, so if I have 100,000 adverts in my database, then my arms is going to be 100,000, because the arms represent what the agent is going to be able to do, the action that is going to settle on. So if you are building this for let's say clinical trials of new medication, then the arms is going to be the number of new medications that you want to try on patients, or the number of new vaccines that you want to try on patients. So I really hope you get the understanding very well. Okay, and I'm also going to create reward probes, and this I'm going to spend some time to really explain it very well to you. And I'm going to make it it's going to be randomly generated probabilities. And so at this point I'm going to stop here so I can take time to explain to you what the reward probabilities are. And for that, I'm going to create an environment. So I'm going to create an example of the environment, and I'm going to say my arms is equal to 5. So let's just say we have 5 arms, and let me print the environment dot reward probes, and then I'll take time to explain here. Okay, so I have created this 2D matrix which I call the reward probes, and is actually a matrix that stores the reward probabilities for each state and action pair. In my example, my state is every row. Okay, so every row in this matrix represents a state. So this is state 0, this is state 1, state 2, state 3, state 4. And each column on a row represents the probability of getting a reward if you take that action in that particular state. So state 0, and then this is action 0, the probability of reward for action 0, probability of reward for action 1, probability of reward for action 2, action 3, and probability of reward for action 4. So by just looking at this row, it becomes obvious to you which action you should take when you are in this particular state. And by simple inspection, you can see that the best action is the action that has the 0.554 probability of giving you the reward. Mind you, the focus of the agent is to come up with the best reward, the best cumulative, the biggest cumulative reward in the future. And so the way to maximize that is to take actions that have higher probabilities of giving you a reward. So, in your case, you have to, I mean, in real life applications, you should know that we do not know even the reward probabilities, because if we know the reward probabilities, then we don't need this multi-armed bandit algorithm in the first place. The reason why we need an algorithm that can learn these dynamics of the environment is because we don't know. But for the purpose of simulation, I need to create these reward probabilities so that we can look at the performance of the agent in the context of these reward probabilities and come up with a strategy to know whether the agent is really working or it is not working. Now, I'm going to spend some time here to also explain to you what should be in your state. In my case, my states are just the rows, and by the rows, I don't mean the items in each of the row. I mean row 0. When I say row 0, that is my state. When I say row 1, that is my state. So basically, when the agent sees itself as being in state 0, then it has to take the action that has the higher probability of giving it a reward. And by looking at the reward probability table, you can see that this is the best. So if I come to the next state, you can see that in this case, this is the best action to take, which is action 0. When I come here, you can see that this is the best action to take. So basically, you're just looking at the probability, that the highest probability in each row to determine the best action to take. Now, it is important for me to explain things here for you to understand how to apply this algorithm in the real world. So I'm going to give you some concrete examples of what should go into your state. And I'm going to repeat again that I am creating this environment because we need a simulated environment to be able to evaluate how our algorithm is performing. Okay, in reality, you don't have access to this fine-grained information. Otherwise, we don't need this algorithm. So let me give you two examples, and you will have to form your own intuitions about how to come up with what you have to include in your context or in your state information that is going to influence the best actions that the agent is supposed to take. So let's take, for example, the advertisement space. So let's say you are building this deep contextual MAB to help optimize click-through rates on adverts that are placed on e-commerce websites. Think about it. What are some of the things that should go into the state? What are some of the things that should go into the context? The context is what you show the agent to influence its action. In the previous implementations that we've seen so far, we didn't show the agent anything. The agent basically had to pull things and then learn their average reward rate, and then it kept on pulling the arms that gave the best reward. In this particular scenario, we want to answer the question that given state S, which action A is the best action to take? So with the online advertising example, what can go into the context or the state is the information that you store about the user, which later becomes the user's digital footprint. So for example, you want to store information about the age of the visitor of the website, because people's preferences in life sometimes depends on age. When people are young, they have things that they want. Every child is interested in toys and things that they can play with. When we get into the adolescent stage, we mostly tend to be interested in electronics and gadgets. So you want the latest phone, you want the latest iPad, you want the latest game console, you want the latest device on the market. At that stage, we also tend to become interested in fashion. You want the nicest dresses on the market, and you want to dress to match. These are all things that people in their old age mostly do not care about. Like when people are old, they mostly do not care about dressing to match and the latest gadget in town. They care more about things that are only important to them at that stage. Okay, so the age also becomes important to be included in the context of the state information. Another thing that you want to look at apart from the gender is, apart from the age, is the gender, because boys and girls tend to be interested in different things at different stages of life. So that is also an important information that goes into the state. Another thing that you want to take into consideration is the geographical location of the person, so that if, let's say, I am visiting an e-commerce website in Africa, then you need to know which advert to show me that will be relevant to somebody visiting that particular website in Africa. It might be different from somebody visiting that website in, let's say, America or Europe. So I am sure by this point you are recognizing that the state is not one piece of information. It's actually a group, okay? So it's an amalgamation of different information that goes to form a vector that becomes the state. And in this particular example, I want a very simple environment. So our state is just going to be 0, 1, 2, 3, 4, 5, all the way to 9, because I'm going to let us use 10 amps over here. And by the use of the one hot encoding function that we created, so this is now when you begin to realize why we needed this. By the use of the one hot encoding, we will be able to encode our categorical state labels, which is 0 to 9, into a vector of dimension 10. And the only item in that vector that is going to be 1 is going to be the position in the vector that refers to the categorical label that the state refers to. So as you can see here, for state 0, it's going to be 1, 0, 0, 0, 0, 0, 0, 0, and it's going to be, the dimension is going to be the number of arms that we choose. Okay, I'm going to give you another example. So if you are using this for task assignment, let's say to assign courses to faculties in your department, what you can do is you look at information that is important to determining whether a faculty is going to perform well when assigned a particular course to teach. And some of the things you can look at, of course, you can look at the years of experience of the faculty, and you can also look at student ratings, like existing student ratings of that particular faculty for various subjects. Okay, and so you have to be creative about what you include in your state information. And one clue that I can give you is whatever you include in your state information should be information that can influence a human being's behavior. So if you gave this piece of information to a human being to take a decision based on that, do you think a particular information in the state is going to be important to influence the action that the human being is going to take? If it is important, then you can include it in your context or your state information to help the agent to also learn associations between the context and the optimal action to take in the end. And the reason why we are going to use a neural network here is, I am sure you are realizing by this time that the state is going to be infinite. Of course, it is true. It is going to be infinite. It is most likely going to be infinite. It is less likely to come up with states that are infinite. You are lucky if you have states that are infinite, like the simulation empowerment that I am creating here, because it is infinite. It's just 10 states, and the agent can be in any one of them at any time. But in reality, your state is going to be infinite. And because of the infinite nature of the state, that is why it becomes important for us to use a neural network, because neural networks are universal function approximators, which are able to learn associations between even, which is sometimes a downside to neural network. It is able to learn associations between even data sets that are randomly generated. And so when we use a neural network, we can adjust its parameters to be able to learn association between the different state or context informations that it sees and the resulting optimal actions that it is supposed to take. Okay, all right, so enough time has been taken to explain this. Make sure you really understand this point before we continue, otherwise you'll be lost along the way. All right, great. So let's come here and continue the creation of our environment. I'm going to create a method that I call update state. And what the update state function is going to do is to just set a state randomly. So state is equal to mp.random.random int. And so basically I'm just going to generate a random number between 0 and self.arms. Okay, so when you create this environment first, we need to know what state the environment is in. And because everything that has to do with creating the environment happens in the constructor, we are going to call self.update state over here. And mind you, I'm starting the name of the update state function with the underscore to indicate that it is a private function. So it is not meant to be called outside the definition of the environment class itself. Python is not going to enforce it, but by convention in the Python community, when people see this, they know that you intend to make it a private function. So if we have a state, then let's have a method for getting the state. So I'll say get state, and that is also very simple. All that it does is to return self.state. Okay, all right. So mind you, this is a simulation environment. In a real world application, you have to come up with a state, and the state, like I've explained to you, is an amalgamation of different pieces of information that you think are important to influence how the agent or even a human being should take actions based on all those information that you are giving it. Okay, all right, now let's come to how to get a reward. So I'm defining a function called get reward, and that is also a private function. So I'm going to define the function such that it is going to take an arm. So the question is, how much reward do you get when you pull this arm? And like I've told you already, these reward probers, which you are seeing down here, dictate how much reward the person should get, the agent should get for pulling a particular arm. And so you can see that the reward you get depends on the state in which you are and also the arm that you pull. So I use this second row as an example. If the agent is in state 1, so because this is state 0, this is state 1. So if the agent is in state 1, then obviously action 0 is the best action to take because it has 0.93 probability of giving you a reward. If it is in stage 2, then you get to know that action 1 is the best result, the action to take. If it is in the last state, then you can see that action 2 is the best action to take because it has 0.83 probability of rewarding you. So this also influences how you come up with your rewarding scheme in a real world application scenario. So for example, in the case of the optimization of advert click-through using Deep Contextual Bandit, how you come up with the reward for a particular advert is the measured click-through rate. So you measure how many times the advert has been shown and how many times people have clicked on it, and that becomes the you can come up with your own rewarding scheme. These things are not set in stone, so you have to be creative about how to come up with your own rewarding scheme that makes sense to your particular problem. So I will not be able to explain a one-fit-all rewarding scheme scenario. For example, in robotics, you tend to even reward the robot with a -1 reward even for not doing something wrong. And the reason you do that is you want the robot to act faster. So for every time step that it wastes, it loses 1 point so that the robot will learn how to act faster. So the idea of coming up with a rewarding scheme is not a global formula. There's no global formula that you can follow. You have to be creative about it. In our case, I'll first of all check which state we are in. So I did self.getState. And mind you, the state is going to be a number because we over here the function that sets the state is the update state. And what happens is it just generates a random number between 0 and the number of arms that you have defined in the environment. So we have the state. Now let's get the probability. So the probability is going to be self.reward probers. And so we get the probability for that state that state, and that arm. Okay, so it's like we look at the row and we look at the action, and then we get the probability of getting a reward if you take that action. Okay, and what I'm going to do here is a rewarding scheme that worked for this environment. So what I do is I say rewards is equal to, I'm using list comprehension here. So I'll set 1 if mp.random random is less than probability, else 0 for underscore in range solve.arms. If this code here is a problem for you, then you want to learn about list comprehensions in Python, but I'm going to try to explain to you here. So basically what I'm doing is I'm generating a random number, arms number of times. So if arms is 10, then I'm generating random numbers 10 times. Okay, I generate random numbers 10 times. And anytime that the random number is less than the probability distribution for that particular state action combination, then we get 1. We add 1 to the list. Otherwise, we add 0. So the total reward here is going to be just the sum of the rewards list that we've created up here. Okay, so in order for you to understand this environment, I'm going to play with it once more for you to see. Okay, so now we are in this environment, and this is the reward probabilities. Let's try to get a state that we are in. So we can say state is equal to env.getState, env.getState, and so I'm going to print the state first, but then I also want to know the probability of reward for taking a particular action. Now we haven't defined the way to choose an arm, so I'm going to just print the state here. So I'm going to print the state. Okay, so if you call environment.getState, it tells you that you are in state 1. At other times, it can start in any state at all. And you realize that anytime I create a new environment, there is a chance that it's going to start in another state. So previously it was in state 1, and now it started in state 3. And so that is simply because of how the state is calculated. Basically, I just generate a random number between 0 and the number of arms, and that becomes the state that the environment is in. And so that becomes the state that the agent also sees. Okay, now let's define one very important function. We're going to call that choose arm. So choose arm, and then it's going to take solve and arm. So this is where the agent is going to be able to choose that particular arm, which is also the best action as far as the agent is concerned, and it will get a reward for choosing that best action. So I'm going to say reward is equal to solve.getReward, and then we are going to give it the arm. Don't forget that the getReward function also takes in the arm, and this is where we try to see in which state the environment is in, and we do the calculation of the rewards. These are all simulated. Okay, and then inside here, because we have the reward now, we need to update state so that the agent goes into another state. Because if you're in a state, you take an action, you end up in another state. For example, in the e-commerce website, if I'm on the site where they are selling dresses and I see the advert for the site where they are selling shoes, and I click on the advert to the site where they are selling shoes, then I am no more on the dresses website. I am on the shoes website. So to simulate the effect of taking an action in an environment, we have to also update the state that the agent is in, because the consequence of taking an action in an environment is to change the state that the environment is in. So, and then we finally return the reward. Okay, so now our environment class is complete, and so we initialize an environment again. We see that we have different reward probabilities because it's randomly generated, and we see that we are in a different state. Now let's say environment dot choose am, and so I am in state 4. Okay, don't forget that I am in state 4. Now if I'm in state 4 and I choose, so state 4 is 0 1 2 3 4, so I am in this state. Which action do you think will give me the best possible reward? It is action 2, because action 0, action 1, action 2, which has 66% chance of giving me a reward. And mind you that the way we calculate the reward is to loop over, and then when the random number generated is less than the probability, then we add 1 to it. Okay, so over here I'm going to choose action 0 1 2, so I'm going to say choose action 2, and then it tells me that when I choose action 2, it gives me the reward of 2. And now, because we have chosen an action, if we get the state again, so if I say environment.getState, it should change. And so we have moved from state 4 to state 2. Okay, so this is it for the simulation environment that we needed to create so that we have something to play with as far as our algorithm is concerned. Now we want to go on to the point where we are going to build our neural network and use the neural network to learn the association between the different states and the best action to take. Okay, so everything we are seeing here are just preparations towards the actual objective of implementing a deep contextual multi-armed bandit algorithm. Okay, so let's start. And this is the point where your knowledge about PyTorch becomes very important. Sorry, your knowledge about PyTorch becomes very important, because I'm going to use most of the things that I have taught you about PyTorch in this particular video. Okay, so let's start by defining our model. And if you watch the previous video, I've started using the torch.nn module to create neural networks instead of building everything from scratch like we used to do before. So that is what we are going to do from this point onwards. So I'm going to say model is equal to torch.nn. In fact, I don't need to do torch.nn because up here we've already imported torch.nn as nn. So I'll just say nn.sequential. But first of all, let me start by defining the number of arms. Okay, so I'm going to say n arms is equal to 10. So I'm going to have 10 possible states and 10 possible actions. Mind you, you need to change things for your own custom implementation of the algorithm. And so I'm going to say model is equal to nn.sequential. And what this nn.sequential does in PyTorch is to help us to define different layers of the neural network. Okay, so we just add them in a sequential manner, and so the data is going to flow also in a manner in which those layers are defined. And we have already done a video to talk about the nn.linear. That is what we are going to use in here, because this is a very complex problem to solve. So I'll say nn.linear, and because my one hot encoding is going to be the encoding of the state, so like over here you can see that I'm in state 2. When I'm feeding the state information into the neural network, I've already explained to you that you don't want to feed in these categorical labels into your neural network, because the neural network is going to learn to associate importance to these categorical labels based on their values. So if you make that mistake and you feed in this state information directly into the neural network, what's going to happen is the neural network is going to think of state 4 as a more important state than state 2. Meanwhile, in the actual context or the problem you are solving, that is not how things are supposed to work. And so before I feed in the state information into the neural network, I'll use the one hot encoding function that we created up here to one hot encode it into a vector of 10 dimensions, where the only position that will have the number 1 is going to be the position that refers to the state that the agent finds the environment in, and the rest are going to be zeros. And so the input to our neural network is going to be 10, because our n arms is 10. So I can actually write n arms here. And so I want I want 10 inputs to go, and I want my hidden layer to be, let's say, 100. I mean, feel free to play with the number of the hidden layer, because there could be a correlation between the size of the hidden layer and the performance or the accuracy of the neural network as far as the problem at hand is concerned. What is going to happen is, after the first linear transformation, we will run the ReLU activation function on it, and I have also done a video in the past explaining what these activation functions do, so I'm not going to repeat myself here. And I'm also going to pass it through another linear layer, and because the output of the ReLU is going to be 100, because the hidden layer is 100, then the input after the first layer to the second layer is also going to be 100, and so I get 100, and I want to generate 10 possible values for the actions. So let me say here n actions is equal to 10. So the reason I'm doing this is because the way I initialize my reward probabilities in the environment is that the table is going to be arms by arms. So if your state is 10, then your actions is also 10. And I explained that is for simplicity's sake. You don't have to necessarily do this for your own use case. Always try to find out how many actions are there in your possible, how many actions are possible in your problem at hand, and just use them. Okay, so I'm going to pass it through another ReLU layer here, and this is going to be my neural network. This is a very simple neural network. It's actually just two layers, 10 coming in, and then the hidden layer is 100, and then the 100 becomes 10 output. So the output is going to be the neural network's prediction for the possible reward for each of the actions that you can take. Okay, so now I'm going to just print out the model so that you see what's in the model. So it's as simple as that. We have a linear layer, 10 goes in, it becomes 100, passing it through a ReLU activation function. 100 comes in, it becomes 10, you pass it through the ReLU activation function. And the reason why I'm choosing the ReLU activation function is, and not any of the sigmoid and the softmax and all those things, is because of the nature of the problem. The nature of the problem is such that we want to build a neural network, okay, that will take in the state information, and the state information is one hot encoded. So if you take in the one hot encoding of the state of the environment, and the neural network will try to come up with a reward prediction for each of the actions. Okay, so what the neural network is going to do is going to come up with a vector that looks like this, but the content of the vector is to be interpreted as the reward you will get for taking any action in that particular state. So when you have 10 actions, the vector is going to be made up of 10 items, and each index is going to be the neural network's prediction of the expected reward for taking that particular action in the given state. Okay, all right, so now let's create a fresh environment, and let's use the environment to do our training and stuff like that. But before that, let's build the training loop, and then we'll see how the algorithm works. So I'm going to define a function called train network. So the train network is going to take, first of all, an environment. So I'm going to call my environment E. I don't like the name E, but I have already used env up here, and I don't want you to be confused about it, so I'm just going to call it, okay, I'll call it environ. Okay, environ should be fine. All right, and the next thing we're going to take is our neural network, and the epochs, the number of times we want to train this algorithm or the neural network. So I'm going to default it to 8,000 epochs, and we also take a learning rate, and I'm going to set the learning rate to a default of 1 times 10 to the power negative 2, which is 0.001. Feel free to play with different values that works for you. Okay, so what we do is we create our optimizer, and if you don't understand anything from this point, then you really definitely have to go back to watch the last 2 videos before this video, because that is where I showed how to use all these APIs of PyTorch to make our lives easier. So I'm going to use an optimizer called Adam. I haven't yet explained the different optimizers. In the previous video, I used SGD. Now I'm going to use Adam, but we have dedicated videos. Feel free to use whichever you want, but Adam is a pretty good optimizer, so feel free to use it as a default until I make a video to explain everything. And the optimizer is going to work on the parameters of the network that we pass in, and the learning rate of the optimizer is equal to the learning rate that we pass in. Okay, now let's create our loss function, which usually is known as criterion in PyTorch. Okay, so I'm going to call this criterion. Criterion is basically the loss function. That is how things are called in the PyTorch community. So I'm going to use MSC loss. From the previous videos, I use the MSC loss from the functional interface. They do the same thing, but the way you call them are different. So basically, I'm just going to use MSC loss, and I'll explain it along the way. All right, so let's have a list that is going to store the rewards that our agent will be making along the way. And then I will say for epoch in range, I'm going to start from 1, and because I'm starting from 1, I have to add 1 to my epochs, because usually counting starts from 0. Okay, so now the first thing we want to do is, we first of all want to get a state, okay? The state that the environment is in, because this is how you also train your algorithm in the real world. So like in the advertisement example that I've been giving, the neural network has to be presented with the state, which is the context information, which is the digital footprint of the user who has visited the website, and it contains every information that can influence what adverts the user should see. So in our case, the state is just what state the environment is in, but we are going to want hot encoded because of obvious reasons that I've already explained. So I'm going to convert that into torch.tensor, and because this is PyTorch, we are dealing with tensors instead of NumPy arrays, but they are very similar in the way they work. Okay, so I'm going to call one hot encode, and then I'll say my environ dot get state. So I'll call the get state function of my environment so that we know which environment we are in. The next thing we want to do is we want to get rewards prediction. So like I explained to you, the neural network is going to try to predict the possible rewards for taking each action in the state that you are presenting it with. So we pass in the state over here. So you get a state, you pass it into the neural network, and the neural network is going to return a tensor, and the way you have to interpret that tensor is that the values of the tensor represent the neural network's estimation of the reward that you are expected to get for taking each of the possible actions in there. Now, one thing you need to take note of is, because the parameters of the neural network is initialized randomly, at the start, the neural network is going to operate randomly. And so the question is, how do we correct the neural network? Because this is a randomly initialized neural network parameters, and so the neural network's predictions or the estimations of the expected rewards are also going to be random. And so how do we come by the possible way to teach the neural network so that it will make adjustment to its weights or the parameters, so that the next time it sees a context that is similar to the state we are passing it in, it is going to make the best it's going to make the perfect prediction. Okay, the way you do that is, first of all, let's convert the rewards prediction into probability, because mind you, the action that the agent is supposed to take, we want to merge exploration and exploitation, like you saw in the previous multi-arm Bandit implementations. Like, let me look for an example here. So when it comes to choosing the arm for epsilon greedy, you can see that we do np.random.choice, and usually the choice is guided by the probability distribution for each of the arms. So that is what we want to do in here. So we want to convert the reward predictions into probability distribution over the possible set of actions. Okay, so what we do here is, Now we have the rewards prediction. So what we do here is we say actions probability or action probes. So the probability that the agent should take each of the actions. So action probes is equal to softmax, which is a function that we have already defined and I've explained what it's supposed to do. And we are going to call rewards prediction dot data dot numpy. I'll explain why I'm doing this. The numpy dot copy. And the reason why I'm doing this is if you look at the implementation of the softmax function up here, you can see that the softmax function expects to receive as data ND arrays, which are numpy arrays. But because we are using PyTorch and we send a PyTorch tensor into the neural network, the output is also going to be a PyTorch tensor. And so when I call .data.numpy.copy, basically I'm just copying the underlying data from the tensor and I'm passing it into the softmax probability function. Okay. All right. So now we know the probability over the probability distributions of the action space. What we want to do is what arm are we supposed to choose, and that is np.random.choice np.random.choice, and it's going to make n arms choices. We've already defined n arms to be 10. Okay, so it's going to make n arm choices, a choice from n arms, and it is going to use the probability distribution that we have already estimated up here. So action probes. So this is not different from how we chose arms in any of the classical multi-armed bandit algorithms that we know of up until this point. Okay, so now that we have the arm, let's actually choose the arm and get the reward. So reward is going to be our environment dot choose arm. So we choose arm by stating the arm that the agent have selected and we get the reward. Let's append the reward to rewards. So let's append reward to rewards. Okay, so now the agent have come up with the best arm to choose. We've chosen it, we've obtained our arm. The question is, how do we teach the neural network to learn the association between the different states and the best actions to take? Okay, so the agent suggested that these are the reward predictions. We turn them into action probabilities. And now we know the actual reward because you see, the agent first of all came up with its prediction, which is here. And we have gone ahead to choose a particular arm. And so now we have the true reward. So you see, this is reinforcement learning, but we are combining it with supervised learning. So the rewards prediction here is what the neural network thinks should happen. And the reward here is the true label, the true reward we get for taking that particular action. And so now is the time for us to let the neural network know that, dude, you said we should take this action and we'll get this reward. However, when we took it, we got this reward. So you need to adjust your parameters so that next time when you are making such a prediction, you'll be more correct. And the way we do that is we have to, first of all, create a new true label vector that we are going to use to evaluate our loss, and the backpropagation we use the loss to update the parameters. So I'm going to say rewards or true rewards. So I'll say true rewards, and then we have to compare that with the rewards predictions that it came up with. So the true rewards is going to be rewards prediction. We are going to make a copy of the rewards prediction. So I'm going to say rewards prediction dot data dot numpy dot copy. Okay, and then we will say true rewards for that particular arm, because that is the only arm that we pulled. For the rest of the arms, we don't know what the correct prediction is. So we only set for the arm whose correct reward we know. So it's like, make a copy of what the neural network suggested that we will get. And then only set the true value for the arm that you actually pulled. We don't mind, we don't care about the other ones if the neural network is getting it wrong. By virtue of exploring, we will get to try all those arms and we will make the corrections as time goes on. Mind you, we are doing this training for 8,000 epochs. That is a lot of time for the neural network to have met almost every situation and then make the correct adjustments to the parameters. So now we set the reward for just the correct arm. And now we come here and we say our loss is equal to our criterion, and then we pass in the rewards prediction. So the rewards prediction, and we create a tensor. Mind you, the copy we made was a NumPy ND array. So now we want to create a tensor from the true rewards. So a tensor from the true reward. And that is how the neural network is going to evaluate how wrong it is. Okay? And then we come down here. And if you want to keep track of your losses, you can do that. So let's say I have my losses here. And so now that we have the loss evaluated, what I can do is I'll say losses.append. And because loss is a tensor with just one item, I can say loss.item. And that should give me the loss for this particular iteration. Okay, so now that we've evaluated the loss, what do? We get the optimizer to 0 grad. And we want to 0 grad because we want to zero out all the gradients it has calculated for the different parameters. Okay, so optimizer.0 grad. And then we say loss.backward. So this is where back propagation is happening. And we will say optimizer.step. And this is where the parameters are going to be changed to reflect what is really happening versus what the neural network thought should happen. Okay, so now that we have this implemented, we can return our losses and our rewards. So say np.array losses, and then so this is basically returning a tuple. So np.array, and then I return the rewards over here. So we have this function that we can call to actually do the training for us. So let's say losses, rewards. First of all, I'm going to create a new environment. So I'm going to say env is equal to environment, and I'm going to say arms is equal to n-arms, which is also 10 because we've already defined that already. So n-arms, okay, so we have this environment. I want a new environment because the environment we created up here we've played with, and I don't know what state it's in, and I just want a fresh environment to start with. Okay, so now I'm going to say losses and rewards is equal to, call our train network function, and we're going to pass in the env, and the network is going to be the model we created up there, and every other thing we are leaving the default values for. So we are training for 8,000 epochs, and the learning rate is 0.001, and everything should be fine. So if there is no problem with the code we've written so far, then this should work. Why is this not working? So one hot encode missing required positional argument dimension, and that is true. So when we are doing the one hot encoding, let's see how we define it up here. So up here, it takes a position and a dim, and we didn't pass in the dim. So we do the one hot encoding over here. So one hot encode this, and so we need to pass in the dimension, and the dimension is equal to 10, which is also n-arms. Okay, so now let's run this, and hopefully if that has been fixed, we shouldn't have any issue going forward. And let's see what's happening here. So the training is happening for 8,000 epochs, and it has finished doing that now. Let's go ahead to plot. So I'm going to say plt.plot, and I'm going to call the running average function we created here to smoothing the rewards. The reason why we need to smoothen it, I will explain to you. I will take it off, and then we'll smoothen it. Okay, let me first of all start by just plotting the rewards over here. I'll say label is equal to average reward, and I'll say plt.legend. So let's see what we get. So this is a very disturbing graph for us to see, because there are a lot of moving parts in there, and the size of the graph itself is not big enough for us to see what's going on here. But what is actually happening is, because the neural network start off as being random, there are a lot of random things happening, and that is why we need to smoothen out this curve. Okay, so I'm going to call the running mean on the rewards, and I'm going to set a window size of, let's say, um, window of, let's say, 500. And let's see what happens when we do this. So now we can see a proper progression of our rewards, and it is clear that the neural network actually started off not knowing anything, and so it was not making much average rewards. Mind you, this is the average rewards, and for any multi-armed bandit algorithm, our expectation is that the average rewards that the agent is getting will keep rising up until the point where it will plateau, because the agent has learned enough about the environment. And so, as a proof of what we have done with the contextual bandits, you can see that yes, by doing trial and error, by trying to predict what reward you get for taking which action in which state and correcting itself, the neural network has actually learned how to form an association between a particular state and a particular reward. Okay, and hence it is telling us which action we are supposed to take. So to prove things, I'm going to print the reward probes. So env dot reward probes over here, and I'll do the training afresh. I will create a network afresh. So I'm going to start with a fresh network actually. So I have a fresh network here. I print out, which is not important, define the training function, and now I have printed out the rewards probability over here, and actually let me also print out the state. Okay, so I'll say print, I'm going to do f strings, and I'll say current state. So current state, so the current state is going to be equal to env dot get state. Okay, so we print the state as well. I want to prove a point here. So we have this, we run it, we run our model, training function, we define a new environment, we are in state 5. Okay, and then we run our training, which is going to do that for 8,000 epochs, and then we plot, and yes, we see that there is a natural upwards graph, which means the agent is learning, and there are some randomness in there. So the agent is not only exploiting, but it also has the chance to explore. That is why there is some randomness in there, and that is actually good, because it helps the agent not to settle on an action that is suboptimal as far as that particular state is concerned. So we run our model, and so this started off in state 5. So this is state 0, state 1, state 2, state 3, state 4, state 5. And so the model is predicting that if you're in state 5, the best action to take is so these are our rewards probabilities, and so it appears the best action to take when you are in state 5 is the last action over here, which has the probability of 0.9847 rewarding. Okay, so if we invoke our function, let's invoke our model for state 5, and let's see. So I'm going to say rewards, let's say predictions. So I'll say predictions. First of all, let me encode state 5. So I'll say state is equal to torch.tensor, and then we call one hot encode for state 5. And then I am going to do predictions is equal to our model, and let's pass in the state, and let's print out our predictions. Let's see what's going on here. So okay, once again I forgot, so I'll say dim is equal to 10, and then I run this, and you can see that of course it wasn't too wrong, but it is realizing that when you are in state 5, it appears this is the best action to take. And trust me, because there is also the action of randomness in there, the agent is not always going to take the best action. But then the truth is, it helps to combine exploration and exploitation. And the whole idea here is to use a neural network to be able to learn. So let's run it one more, and that should be the end for today's tutorial. So I'm going to run it once more. Get a model. And the reason I'm running it multiple times is to prove to you that regardless of whichever parameters or the way in which the parameters of the neural network is initialized, we still get to the point where our neural network has learned well enough to be able to know the association between the different states and the environment. So before I end this video, I want to recap that up until this point, we didn't know how to build a multi-armed bandit algorithm that takes into consideration a context or state information. And the state or the context here is just an amalgamation of different pieces of information that are important to influence the actions that the agent is to take based on the particular state. Okay, so with the combination of a neural network and taking into consideration the state, we are able to build an agent that doesn't just pull arms and then estimate the payout rate, but is actually able to take into consideration the state information, the context of the problem, and then to decide the best information. And I remember I gave an advice that the definition of the state, or what goes into the state, cannot be, there isn't a universal formula for doing that. You have to think about your problem very well and determine what should go into the state. Ask yourself, if you are a human and you are supposed to solve the problem at hand, what are some of the things you will look at? If you are a human being whose work is to select adverts to be placed on e-commerce websites so that you increase the click-through rate, what are some of the things you look out for? I explained that the age of the person visiting the site is important because children are interested in toys, adults are interested in gadgets, and very old people are interested in different things. The gender can also play a role because even at different stages in life, boys and girls are interested in different things. The geographical location can also influence that. Even the salary that somebody takes can also influence their taste on e-commerce website. If you don't have enough money, there are certain things you can want, but you will not even attempt to buy because you can't afford them. So these are all things that you have to think about and then come up with a good state definition that you need. Once you have been able to define a good state, the next thing you want to come up with is how do you define the rewarding scheme? Once you have been able to come up with a rewarding scheme, then the sky indeed is the limit because you have neural networks at hand which are able to learn associations between two different data sets. And so the neural network will be able to learn the association between the state information and the best reward that is expected to be taken, so that your agent will eventually, like you are seeing here, eventually be able to give you the best expected the maximum cumulative expected rewards in the long run. So thank you very much for watching this. Don't forget to invite your friends. Don't forget to subscribe, and I will see you in the next video.